appear brighter.
Type 1a supernovas are always consistently brilliant, no matter where they occur in space.
A supernova is the colossal explosion of a star at the end of its life. It just goes kabam! And it occurs when a dying star known as a white dwarf goes through a nuclear runaway and just literally blows itself to smithereens. We find the Type 1a supernovae in very distant galaxies, so they look really faint, and then we compare them with Type 1a supernovae in nearby galaxies whose distances were measured using Cepheid variables or some other technique.
Using these Type 1a supernovas, two different teams set out in the 1990s to measure the deceleration rate of the universe. But to capture supernovas as they occur, astronomers had to put the universe on surveillance.
You can compare this a little bit to perhaps surveying a casino. So all these cameras are on all the time, and most of the time they don't find much of anything interesting, but occasionally they find what they're looking for. You have to look at lots of galaxies. So what we did is we took large telescopes with cameras that have wide fields of view, about as wide as, say, the width of the full moon. And we took many snapshots of space using this wide field camera. And each snapshot contains tens of thousands of galaxies. And by comparing the apparent brightness of the distant Type 1a's with those of the nearby Type 1a's in nearby galaxies, we can get the distance of the distant galaxies and hence the amount of time that we're looking back in the history of the universe.
After the two teams studied the results of 60 Type 1a supernovas, scientists were shocked at their results. The universe wasn't slowing down, its expansion was speeding up.
We all expected that expansion to be slowing down with time, because after all of the galaxies are pulling on one another.
We were so confident we were going to measure the rate at which the universe was slowing down, and then we found, of course, a negative answer. The universe is not slowing down, it's speeding up, and this was just a big mystery.
That is really, really weird. You know, we expected to measure some amount of slowdown, and instead it's expanding more quickly. That's like the wrong sign, right? We were really afraid that we had gotten completely the wrong answer. We rechecked our measurements, we checked the analysis. A bunch of people on each of the two teams did the measurements and the analysis independently and kept getting the same result.
One of the greatest shocks in the world of cosmology just in the last few years has been the realization that our universe is accelerating.
This repulsive force driving the universe was called dark energy, an invisible energy that was nothing anyone expected or understood.
It suggests that over the largest distances in the universe, there's a repulsive effect that dominates over gravity.
And dark energy was creating space, taking galaxies along for the ride.
This energy that appears to fill the universe and stretch the expansion of the universe faster and faster with time is now known as dark energy. So here I throw the apple, and initially it's decelerating, and then dark energy makes it accelerate away from me. So you throw the apple, and it just zooms away faster and faster with time.
Like the apple forever traveling into space, galaxies are being carried away as more space is created.
So if you could imagine, a classroom populated by chairs, and those chairs are slowly getting further apart from one another within a classroom. Because if all the chairs are being stretched apart, like in the expanding universe, no matter which chair you sit on, you will find all chairs are moving away from you. So the chairs are not really expanding. In fact, the chairs are the same size, really. What's happening is that the room is getting bigger. The space in between the chairs is being stretched apart.
more space is being created in between the galaxies. So you have individual galaxies remaining of constant size in a universe where all of space is getting bigger and bigger.
Dark energy is very different from dark matter.
It doesn't clump up like galaxies do in clusters or like stars do in galaxies. Instead, it appears to be pretty uniform, and we find the same amount of acceleration no matter which direction we look at.
It's probably smooth, although some people believe there may be structure in its distribution and its influence.
Dark energy is the energy of the vacuum, the energy of nothing. Even nothingness has energy, and it's pushing the galaxies apart, creating a runaway universe.
It appears dark energy and dark matter have been at war with one another since the beginning of time. Science believes dark energy was created along with dark matter at the moment of the Big Bang. It has always existed in the universe, but gravitational forces of dark matter kept it in check, slowing down the expansion of space during the first 9 billion years of time. This changed 5 billion years ago when the universe grew big enough so that dark matter was dispersed throughout the universe, and dark energy wasn't so affected by dark matter's pull. As a result, the universe began to expand at an accelerated rate.
Dark energy is a constant term. That was probably very insignificant when the universe was hot and dense in the beginning, and so it doesn't really matter whether dark energy is there or not. It is there, but it just plays no role at all. And then as the universe gets cooler and less dense and bigger, so gravity becomes less important, and then dark energy takes over. It's a property of space that we don't yet fully understand.
As the universe expanded, astronomers realized dark energy won its struggle with dark matter and started the acceleration 5 billion years ago.
So there came a time, about 5 billion years ago, when the dark energy started dominating over the attractive matter in the universe. So in a sense, if you plot the force versus time, the gravitational attraction is declining with time, the repulsion is increasing with time, and about 5 billion years ago, the two curves crossed, and that's when the universe started accelerating in its expansion.
Dark energy is fundamental to understand because it tells us where the universe is going. What's the fate of the universe? Is it going to expand forever and get cold and dark? Or is there, some end in sight?
Dark energy now drives the expansion of the universe, and it doesn't seem to be stopping.
The repulsive effect of the dark energy increased because the more space there is between galaxies, the greater is the cumulative effect of the dark energy, the repulsive effect.
And individual galaxies seem destined to a lonely existence.
So it looks as if this is the end of everything.
Surprisingly, the theory of dark energy was proposed and discarded long ago from one of physics' greatest minds. He called it his biggest blunder. His name was Einstein, and he might have been onto the greatest discovery of the 21st century 80 years before anyone had a clue. Science now understands that dark energy is creating and expanding space. But in the early 20th century, astronomers believed the universe was only as big as the Milky Way and would never grow in size. But Einstein had just formed his theory of relativity and decided to test it on the static universe. But as hard as Einstein tried, he could not balance his equation to equal a static universe. His calculations showed a universe that must either expand or contract.
He realized that if you had a universe that was smooth, that was uniformly distributed with stuff, his theory unambiguously predicted that it should either be expanding or contracting.
So Einstein proposed a repulsive vacuum energy that would hold the universe in balance with attractive gravity. He called it his cosmological constant, a constant energy that would hold the universe in balance.
He introduced the cosmological constant, or dark energy, to hold the universe static.
When Hubble announced space was expanding, suddenly Einstein's cosmological constant seemed irrelevant, and he labeled it his biggest blunder.
Now it turns out that dark energy, the concept that he threw away back in the 1920s, is in fact the dominant force blowing the universe apart. Einstein's so-called blunder will eventually determine whether or not the universe dies in fire or ice. And the betting is the universe will die in ice.
In trying to survey how the universe behaves, Einstein had erroneously predicted dark energy and what is the total makeup of the universe.
The total amount of stuff in ordinary matter and dark matter is not enough to account for the curvature of space that we observe.
Like looking across a horizon on Earth, the size of the universe is so great the curvature of space appears flat.
Add ordinary matter, and dark energy together. That makes a prediction for the curvature of space, and that prediction comes spot on. You get the right answer.
Our satellite data now has revealed the fact that 73% of the matter-energy content of the universe is dark energy. Dark energy, which was once Einstein's blunder, is now known to be the dominant force in the universe.
His blunders are our great discoveries.
Scientists are at the very beginning of understanding what effect dark energy will have on the fate of the universe.
Ideally, we'd like to measure how dark energy is behaving as the universe ages.
Eventually, when the dark energy completely dominates over dark matter, the universe will enter a stage known as exponential expansion. For every given unit of time, it'll double in size. And unless the dark energy changes sign someday and becomes gravitationally attractive, the fate of the universe is to expand forever, more and more quickly with time.
We don't understand, if the vacuum energy is driving the acceleration of the universe, why it has the amount it does. That is one of the deepest puzzles remaining in theoretical physics today.
Trillions of years from now, it's going to be a very lonely place. We'll look up in the sky, and the skies will be practically dark. The oceans will freeze over, and it looks as if this is the death of all intelligent life. It looks as if dark energy and the laws of physics are a death warrant to all intelligent life in the universe.
In discovering dark matter and dark energy, science is one step closer to defining the theory of everything. One equation that will define the entire workings of the universe.
Once we have the theory of everything, we'll be able to answer some of the deepest questions ever since man and women first looked at the heavens. This could be the crowning achievement of 2,000 years of investigation into the laws of nature ever since the Greeks asked the question, what are things made of?
For now, dark matter and dark energy continue to be the greatest cosmological questions of the 21st century.
It's certainly frustrating, yes. I mean, it's humbling, too, to know that, all we know about physics is restricted to normal matter, and yet there's all this other dark matter and dark energy that we really understand very little about.
It's the beginning of a new era and the mysteries of the dark side of the universe.
It's the Wild West as far as particle astrophysics, which is what we call this field.
It's a property of space that we don't yet fully understand.